All right, so I'm going to go ahead and share my screen so we can take a look at Canvas. I know it's just the beginning of the second week, and so we might not all know where things are, so I want to make sure that we know where to find things if we need to. All right, so okay, so on Canvas, a few things. There are announcements sent out every week, right? So when we click on the announcements, these go directly to your email account, I believe, whatever is linked to Canvas, but you can also come back to Canvas and read it here if you're not an email checker kind of person, okay? So this is our La Semana. Every week we're gonna have an announcement that is sort of like the overarching details of the week. So for this week, these were our main announcements. So Friday, okay, Friday the 21st was your last day to drop without a W on your transcript. Since that day has passed, you'll have until September 18th to still withdraw if you're like, oh, this class is really not working out for me, okay? So the first deadline is usually pretty fast. In a regular semester, it's 2 weeks. And then the withdraw deadline is usually about 2/3 of the way through the course, okay? So remember, if you do withdraw though, you'll have a W on your transcript. And so that's something really important to maybe talk about with Patty, who is the STEM core. She's a STEM counselor. She's really, really helpful with not just making sure you take the right classes, but what to do if something's not going as well as you want it to go, okay? All right, the other thing I said in the announcements was that you have exam 1 coming up, all right? So our first exam is gonna be on Thursday. Now I know we don't normally meet on Thursday, but this is going to be, you'll have a 24-hour window within which you can open the exam. Okay, so now as soon as you open that exam though, you have 2 hours, the clock is running, you have 2 hours to finish that exam, and that's it, okay? So you can't like do a question and then come back to it a few hours later, you only have 2 hours for the test. Now that exam is gonna cover 4.1 through 4.7, as well as parent functions, which we're gonna talk about today, okay? I know this is a fast-paced course, so my goal is not to make you guess what I'm going to be putting on exams or what's important, but all of the lecture materials, the homeworks, the quizzes, the classworks, they're all meant to feel relatively similar to what I might ask on an exam, okay? I do expect that you use methods that we learned in class to answer the problems. I know that there's often more than one way to solve a problem, but if I'm highlighting a specific method and I talk about it like over and over and over again, it's probably because that method will be useful in the future for you, not just in this class, but it might be helpful when you get to Calc 1 or Calc 2 or Calc 3. So I really want to set us up to learn the things that will give us the most bang for our buck in the future, okay? I'm really, really big on making sure that you show your work, okay? So if I ask you to show your work or use techniques that are in this class, please stick to that. If you sort of skip a lot of steps, then you're leaving me to wonder like how you got from one step to the other, or how you plugged in the wrong numbers but magically got the right answer. And that's not a guessing game I really want to play with you folks, okay? So make sure that you make it really clear where you got what from. In case you haven't taken a look yet, I did post an exam 1 topic list under the exponential and logarithmic function module in Canvas. I'm going to show you where that is after we go over the other announcements, okay? All right. Week 2. So this week we're going to be covering 4.4, 4.6, and parent functions today, and then 4.5 and 4.6 on Wednesday. You do have 2 quizzes due this week, okay? So 2 quizzes is the norm. I know a couple people missed that second quiz, but every Wednesday, every Friday, the deadlines are gonna be the same throughout the entire course. So just put it on your own calendar every Wednesday, every Friday, this is what we gotta do. Exam 1, again, that opens at 9:30 a.m. on Thursday, so that is the earliest that you can start it, and it closes at 9:30 a.m. on Friday. Now, I really just want to make that clear. If you go in to take the exam at 9:29 on Friday morning, it closes at 9:30. So you got 1 minute to do whatever you can do, okay? It's really up to you to make sure you know when the exams are, that you don't miss the exam day, and that you leave yourself enough time to finish that exam, okay? Support. So I know that we're still fairly early on in the class. I know that there are some study groups going on. So if you are not in a study group already, then maybe reach out to some folks in the chat during class and just make sure you get connected with some folks, okay? These are folks that, again, my hope is that we're all in this, and we're all in this all the way through the end of Calc 1. Okay, if we can all get through Calc 1 by the end of your first year here at Mesa, that would be so amazing and really allow you to access a lot of those upper level classes, okay? So those are resources that you can do on your own time. Attend Val's tutoring sessions. So Val really, really knows her math super well. If you showed up to her tutoring session last week, I think you realize that she really knows a lot and she explains things pretty well. But in addition to that, she and I meet on a weekly basis. So she knows like how I teach, what I expect on exams. So she's not just like a random tutor who's like, oh, teaching you how to do this stuff and it's not connected to class at all. Like, she and I talk regularly, so her support is meant to be targeted for you in this class, okay? Or you can stop by my office hours. So I know they're before class, which is sometimes a little early for some of us, but that's my job. My job is here to support you to be as successful as you can be. And so if you can make time to stop by, that helps me get to know you, know what kind of questions you have, but also figure out ways to maybe like explain things a little differently in lecture so that maybe you understand them better, okay? And one last announcement for this week, which is that after exam 1 has been graded, so it's my hope to have them graded by the end of Friday, okay? I don't like to let things lay around and be ungraded because otherwise I never do them. So I'm kind of on the opposite end where I try and grade things as soon as they come in. So my goal is to have them graded by the end of Friday. And what that means is I'm gonna be placing some time slots on the Canvas calendar so that you can sign up for a check-in with me. Now, I will leave it optional to you whether you want to come check in with me individually or you want to sign up with like a few of your friends in the class. That's also totally fine. Just be aware that during these sessions, I am honest. So if you're not ready to hear my honesty, in front of your peers, then maybe you sign up for an individual session. But if you are totally comfortable with, going over your exam in a small group, you're also welcome to sign up for your session in a small group, okay? Are there any questions on the announcements for this week? So let me show you. Great question. Exam questions are more like quiz and lecture and a little bit less than like the homework. Okay. All right, so 2 things I want to show you real quick. One is, what was I going to show you? Okay, so do you see on the side panel here, I don't know if you ever click on any of these buttons, but the calendar button, okay, if you click on the calendar button, it should bring you to a calendar of all of your classes. And if you're someone who's like not super good at deadlines, look at this. It's got all your deadlines right in here, okay? So it tells you exactly what day and what time things are due. So if you are someone who hasn't figured out a great system yet, or you have too many systems to keep track, this calendar option's a nice place to like find where all your assignments are. And it will populate it not just for this class, but whatever other classes you're taking should all be in here, as long as your professor has put in the assignments in the gradebook already. Okay, so like I've put in pretty much all the assignments for the semester, so most of our assignments have their deadlines here already. When I put in days or time slots for the check-ins, you'll see it pop up and you'll be able to click on it and type in your name, and that's where you can find the sign-in time, okay? All right, one last thing, we're gonna go to the home page. And all right, we're gonna go to exponential and logarithmic functions. So this one, exam one topic list, is new. So if you click on exam one topic list, it takes you to a Google Doc that has the topic. So for example, set up and solve applications of exponential models, and that will be worth 10 points. Graph transformations, parent functions, domain and range for these functions are going to be worth 20 points. And so on and so forth. You can go through, read the topics, and see how many points that they're going to be worth, okay? So as you kind of study, I know the ideal is that we have as much time as we need to study, but I think our reality is that we are often very busy with a lot of other obligations. And so if, you know, if you're looking at this and you're like, I'm just going to study like set up and solve that applications of exponential models and find exponential equations for 2 points, you really only prepared for 20% of the test, right? So what might be a better use of your time is thinking, okay, maybe like solving exponential and log equations together, that's worth 40 points. So that seems like kind of a big deal. Maybe I should make sure to know how to do that, okay? So those are the 2 resources that I just wanted to share with you. Are there any questions on any of the announcements, the topic list, where to find what? All right. Well, then I'm going to go ahead and stop sharing my screen. And we're going to get started on 4.4. Okay, so if you want to go ahead and pull up the 4.4 notes, and I will do the same. Okay. So before we go over 4.4, I just want to say this. I know that I asked you folks to do quiz 2, and there were 2 questions on 4.4, like the very last questions on the graphing. I wanted to see how you would do with those, okay? But if you lost points on those last 2 questions, and after today's lesson, if you want to redo those 2 questions and email it to me, I will update your grade on your quiz. So if you lost points on like the 4.4 questions on graphs of log functions, if you want to redo them after today's lesson and send them to me, you have to email them to me directly. I will regrade them and I will update your grade, okay? So I know there were quite a few people who lost 2 or 3 points just on those 2 questions. But again, if you want to make them up, if you write them out on a separate sheet of paper or a new document, email that to me directly. I'm happy to update your grade, okay? So 4.4, graphs of log functions. So what we know is that we've taken a look at f of x equals b to the x. And we know that this is an exponential function. Okay? And we also knew that this was something that we knew was could determine what all the letters and numbers in certain places mean. So we started off with this really long looking equation over here. And these numbers, all the capital letters, they help us determine the graph transformation that are happening for the function, okay? Now, can someone remind me which letter, A, B, C, or D, are we supposed to use first when we're looking at graph transformation? Yeah, we're looking at that C, right? So C comes first. And a C, if we have a plus C, it means we move to the left. Whereas if we have a minus C, it means we move to the right, okay? And that one comes first. Which one comes next, A, B, or D? B, very good. All right, so B is next. So the B, and that one talks about a horizontal shift, stretch or compression. All right, after that, we had our A value, right? CBA, perfect. All right, and that A value, this A value, that was our vertical stretch. Or compression. And last but not least, we had our D, and that one, if we had a plus D, that moved everything up, but if we had a minus D, that moved everything down, okay? So the reason why we took such a long time talking about graph transformations is because they actually apply to every single kind of function. So this CBAD actually can be applied not just to the exponential functions, but also in this case, the log function, okay? So we've got our log function. And if we were to write it with the graph transformation form, it would look a little something like this. F of x equals capital A log parentheses, capital B parentheses x minus c, close both of them, and then a plus D. And the A, B, C, D talk about the same A, B, C, D that they did in the exponential. So this A in the front, that talks about a vertical stretch or compression for my log function. This B value talks about a horizontal stretch or compression for the log function. This C value talks about horizontal shifts, so we're sliding left and right. And finally, this capital D talks about vertical shifts where we move things up and down. They still happen in the same order, C, B, A, and then D. That part doesn't change, okay? The only thing that does change is we need to think about the shape of a logarithmic function, okay? Now, we kind of talked about this in the 4.3 notes. So let's draw a quick sketch right here of what that log function looks like. Kind of looks like this. And it does, we're going to consider this as like our center point. So this picture is the one that we're going to be shifting left and right, up and down, vertically stretching, and horizontally stretching. All right. So let's take a look at a graph of a logarithmic function, okay? So we're gonna go ahead and pick a few values to plug in for x, but we're not gonna do like we normally do where it's like -3, -2, -1, 0, 1, 2, 3, okay? We're gonna pick some different values that are probably a little bit better for the log graph. And yes, so the coordinates of the center point are 1, 0. So that's actually going to be my center point in the table. If I plug in an x value of 1, I'm going to get a y value of 0, okay? Because I get log base 2 of 1, which really is saying 2 to what power equals 1. And I know that 2 to the 0 power equals 1. So my f of x is 0. All right, so that point we can go ahead and draw on here. We've got 1, 0. Okay. Now, if I wanted to plug in a number for x, log base 2, okay, maybe another good number I could choose is 2. Because what is log base 2 of 2? What is that when I simplify it? It's going to be 1. Okay, and how did you get that? Perfect. 2 to what power equals 2? Okay, so that means when we have an x value of 2, we get a y value of 1. And so 2, 1 is going to be the next point on my graph, okay? What would be another nice number to plug in for x? I feel like 3 is going to give me some weird decimal. What can I get that would maybe give me a whole number answer? 4, I love it. So log base 2 of 4 is really saying 2 to what power equals 4. So I know when I plug in 4 for x, I'm going to get a 2 for y. And if we follow the same format, maybe the next nice number I should plug in would be 8, because I know that 2 to a whole number power is going to give me 8. So when I plug in 8, I get an f of x value of 3. Okay, so let's plot those other points there, 4, 2, and 8, 3. All right, now we gotta go the other way, okay? We wanna know what both sides of that center point look like. So if I think about log base 2 of like a nice x value, maybe I could think of log base 2 of 1/2. Right? That's saying 2 to what power equals 1/2. And what does that give us? When we plug 1/2 in there, what do we get for an f of x value? -1, good, okay. So -1. If I plug in 1/4, I should get -2. If I plug in 1/8, I should get -3. So let's plot those points. 1/2, -1. 1/4, -2. And then 1/2 or 1/8 and -3. Okay. Now, if I start to connect these points, I'll realize that on this side, it continues to go up, but it's kind of going up slowly, okay? So one thing I want us to know is this end does not flatten out, okay? So it doesn't flatten out, but it continues to go up in that direction. And if we connect the other side, we've got something like this, right? Now I think you can tell that those points are going to get closer and closer and closer to 0, but maybe they're not actually going to get to 0, okay? That means that in this logarithmic function, we don't have a horizontal asymptote. So we have a vertical asymptote. So we have a vertical asymptote. And what's the equation of this vertical asymptote? X equals 0, x equals 0. Very good. So we're going to say x equals 0. All right, so we've got our 3 main characteristics here. We've got our vertical asymptote, we've got our center point, and we've got the general shape of our curve, okay? And so that's what we're gonna be looking at when we do the graph transformations, to have the vertical asymptote, have the general shape, and have our center point, okay? So let me change the language here. It says, in general, when you sketch the graphs of logarithmic functions, please include the following features. So let's cross out x-intercept and call it our center point, right? So the center point and the coordinate. So whatever that coordinate is, let's make sure to write it down. So for example, here I would write it as 1, 0. Okay. The general shape, so we want to know that this curve kind of goes down and then doesn't really flatten out, but continues to go up. And we want to make sure that we've got our vertical asymptote, and the equation is x equals a number, okay? All right. So let's take a look at the numbers in the different places, all right? So we did this earlier, but I want us to write it out again one more time. So we've got f of x equals a log parentheses b parentheses x minus c, close them both, and then plus d. And let's see, what did we pick for our colors? We've got our a value, our b value, our c value, and our d value. And that also tells us the order in which we do everything, right? So if we do a C first, we've got our horizontal shift. We do our B second, also talks about horizontal, but this time the stretch or the compression. Okay. Then we move to the vertical stuff. A talks about a vertical stretch or compression. and D gives you your vertical shift. Now, the horizontal ones are what we say they're the opposite of what you think. And what I mean by that is if I see the minus C, it doesn't move in the minus direction, it actually moves in the positive direction, okay? So it's sort of the opposite of what you think it is, whereas the vertical stuff is exactly what you think should happen. So a plus D is going to mean up, a minus D is going to mean down. Okay, an A value bigger than 1 is going to stretch, and an A value less than 1 is going to compress. Okay, so vertical ones, they kind of make sense. They are exactly what they look like, whereas the horizontal ones, I often say, are sort of the opposite of what you think they should be. Okay. All right, let me pause here for a moment before we move on to look at some examples. Are there any questions so far about the graph of the log function or the graph transformation? If A or B is negative, it's going to cause the same reflections that we talked about before. So maybe let's put them in here as well. Okay, so a positive, nope, a negative A is going to mean a reflection over the x-axis, okay? Whereas the negative B will actually be a reflection over the y-axis, okay? All right, so I think that answers Laura's question. And now we have all those graph transformations on one page, one little clip, right? We've got our horizontal, vertical shifts, and then we have horizontal and vertical stretches, but if we just change the sign of those, that's gonna cause different reflections as well, okay? All right, so let's move on to our graph so we can take a look at what's happening, what changes, what stays the same, okay? Okay, so Richard asked a great question. He said, at what point do you reflect? Like before all of the transformations? So you reflect when you get to the positive or negative A. So for example, I would do the horizontal shift first. I would do the pink one first. If there's a horizontal compression or stretch, I would do that one. But at the same time, if it was a negative B, then I would also reflect it then. Okay. And then when we get to A, if the A is negative, then you reflect that one. And when you get to the D, that's the last thing you do. Okay. All right, so let's take a look at these horizontal shifts. So blue and red and green, which one of these is the parent function? Yeah, that red one. And we know that because we've got our center point right there, okay? So we know that this equation for the red one is y equals log of x. All right, let's just assume base 10 for right now so that we don't have to write in a base, okay? What is the equation for the green one? I love it. Log of x minus 3. Very good. Okay. So we know that we're moving our center point. Let's see how far that center point moved. It moved 3 units to the right. And so this minus 3 means 3 units to the right. Okay. Good. So then if we look for our center point here for the blue one, okay, that would make this y equals log of x plus 3. Because we've taken that center point and we moved it 3 units to the right. So this plus 3 is 3 units, I'm sorry, to the left, okay? So the summary here is that x plus c means it moves to the left c units, and that x minus c moves it to the right c units. All right, so what changes and what stays the same? Well, it looks to me like the center point definitely changes. All right, the center point definitely changes. What else changes? The shape, the vertical asymptote. What do we think? Yeah, that vertical asymptote also changes. But what stays the same is the shape of our graph. Okay, so we still have a log graph. That shape stays the same, but our center point and our vertical asymptote move. So if we were to draw in the vertical asymptotes, okay, we've got one right here. This is for the red function. The one for the green function is actually right here. And the one for the blue function is actually right here. Okay. And if we were to write equations for all of these, this vertical asymptote would be x equals 3. This one would be x equals 0. And this last one would be x equals negative. Okay. So moving things side to side is going to change that vertical asymptote and the center point, but not the shape. Okay. So let's talk about these. We're not going to sketch the graph. By the way, this is the first time that I've used these set of notes with students, so that's why I'm like, as I'm going through it, I'm like, ooh, these are things that I like, these are things that I don't like, and maybe we don't need this next time. So thank you for your patience. All right, so f of x log of x plus 1. Tell me some characteristics about this. Where is the center, or what are the transformations that are happening, first of all? Yeah, we're moving to the left one, right? So we're moving to the left one. And if we wanted to prepare ourselves to graph, what would our new center point be? If it was at 1, 0, and I move it to the left, yeah, it's going to be 0, 0. And what's the equation for my vertical asymptote going to be? Beautiful, x equals -1. And I know that it's going to have the same shape that I saw before. Perfect. Okay. All right. So let's take a look at example 3. So we've got log of x minus 5. That means we're going to go to the right 5 units. That means my center point is going to be not at 1, 0, but I got to move that over 5 units. So 6, 0. Okay. And my vertical asymptote is going to be at x equals Mhm. All right, so there is our horizontal translations in a nutshell. Any questions on the horizontal translation? What if x is negative? Okay, so that's where we're going to get to when we talk about that horizontal stretch and compression, when we talk about the negative ones at the end, okay? So that'll be with the reflections when that b value is negative. All right, so the horizontal stretch or compression. So we've got our red curve is our regular center curve again, okay? So this one is going to be our y equals log x. Now the center point for the green one is actually here, okay? So now we're not sliding things back and forth, but what number did I multiply by to get from 1 to 2? Yeah, I multiply by 2. I know that's kind of a silly question. But what that means is when I write it in an equation, it's going to be y equals log of not 2x, but 1/2 x. So a b value of 1/2 will actually stretch it out twice as far. Okay, so that's what I mean by like the horizontal stuff is the opposite of what you think it's going to be. What does that mean the equation for the blue one is going to be? Log of 2x. Yeah, because to squeeze it in half as far, I actually have to multiply by 2. That b value is 2. That's going to give us a horizontal compression of 2. Okay? So if we think about what we could say to summarize, that when b is greater than 1, let's say the absolute value of b is greater than 1, it's going to be a horizontal compression. Whereas when the absolute value of b is less than 1, we're going to get a horizontal stretch. Now, what changes? I think it's very obvious from our blue center points that our center points change. Okay, but does the vertical asymptote change? Yeah, that asymptote is in the same place. So our vertical asymptote stays the same. And I would say that maybe the steepness changes of the graph, but that the overall shape is going to stay the same. Okay. All right, so let's try a couple problems here. Oops. All right, so f of x equals log 3x plus 6. Now I do want to say that in a lot of folks' homeworks that or not homeworks, your quizzes that I was looking at, here's what I saw, and I don't know if you can see my face right now, but I was over the top proud of you for remembering this, because this is probably the hardest thing to remember about graph transformation. But I saw a lot of folks who did this. They were like, log, ooh, Judy said to factor out that number, and then, okay. This is a step that I want to see on a test if you get a question like this, okay? So get in the habit of factoring out the b. So factor out the b. If you do not factor out the b, you're going to get not only the wrong horizontal shift, but you might also get the direction wrong if, like Christina asked, what happens if there's a negative sign, okay? And I don't want you to fall for that mistake. So let's remember to factor out that b. Now, after we factored it, then we can say the first thing we do is we go to the left 2. I don't know what is going on with my handwriting today, sorry. We're gonna go to the left 2, and then we're gonna have a horizontal compression of 3. So that 3, we got to do the opposite of what we think it is actually squeezing in 3 times as close. Where is our vertical asymptote? Okay. X equals -2. Perfect. Okay. All right. Let's try the same thing with example 5. Okay. Let me give you a moment to factor out anything if you need, and then tell me what transformations happened with number 5. All right, so what did we get when we factored out what we needed to factor out for f of x? Left 16, I love that. So log parentheses 1/2, and then we get x minus 16 there. Perfect. Okay, so that means that we're going to move to the right 16, and we're going to have a horizontal stretch, because it's the opposite of what you think, of 2. Okay. Where is our vertical asymptote for this? Yeah, we got the 16 because think about what you need to multiply. 1/2 times what is going to give you the 8, right? So 1/2 times 16 is going to give you the 8. Yeah, awesome. Okay. Ah, yes, Richard, I'm glad you caught that. So here's one thing. When you find your B value or your C value, that actually also tells you where your vertical asymptote is, okay? So that whatever that shift is horizontally tells you where the vertical asymptote is. Okay, so April, to answer your question, if we think about 1/2 and we think about what sort of the opposite of 1/2 is, like maybe a better word for that is reciprocal. The reciprocal of 1/2 is 2/1. So because things that are horizontal are sort of the opposite of what you think, it's not a compression of 1/2, but it's actually a stretch of that value. That make more sense, April? Okay. All right. So we've got all our horizontal stuff, which is the opposite of what we think it is. We did the hard work first. Now we're in our home stretch where we're looking at vertical things. What we see is what we get, okay? So horizontal stretch or compression. If we take a look at all these, all right, they all have the same center point. So we can actually already say that the center point is going to stay the same for a vertical stretch or compression, right? Now, if we know that this red one is our log x, like our parent function, is the blue one a vertical stretch or a vertical compression? Yeah, that blue one is actually, I think I made it easier for myself. It's going to be twice as tall as the original parent function, okay? And then the shorter one, y equals, this is going to be a vertical compression from our parent function, okay? But I think from all three of these graphs, we can tell that the vertical asymptote doesn't change, but that the shape, or rather, not the shape, the steepness changes. Okay, so like a vertical stretch means it's going to go up faster, and a vertical compression means it's going to go up slower. So if we have our absolute value of A is greater than 1, we've got a vertical stretch. And when our absolute value of A is less than 1, we've got a vertical compression. Okay? All right. So we continue layering on. And these numbers should look familiar because these are the exact same numbers as from the exponential graph transformations, because I wanted to show us that it doesn't matter what the function is, it matters where the numbers are. And those numbers, no matter the function, tell us the same thing, okay? So if we take a look at this one, we might recognize, oh, okay, this is a case where I have to factor out that b again. And then I can answer what graph transformations are happening in which order. So we go to the left 2. We have a horizontal compression of 3. And what does that 5 tell us? Yeah, we've got a vertical stretch of 5. Okay. All right. Now, with all of this, where is our vertical asymptote? Yeah, x equals, we're going to the left 2, so -2. Okay. All right, let's take a look at example 7. And the only thing that's different from this one in example 5 is now I've got the 1/6 out front. So log of 1/2 x minus 16, because 1/2 of 16 gives us the 8. And if we identify our transformations in order, we're going to the right 16. We have a horizontal stretch of 2, or the reciprocal of the 1/2. But then when we get to the vertical, it's a vertical compression of 1/6. Okay. And our vertical asymptote would be at x equals 16. So the horizontal stretch of 2 is because our b value, it's the opposite of what you think. And so we're thinking opposite, like a reciprocal. So the reciprocal of 1/2 is 2. So it's a stretch of 2. I know, the horizontal ones always get you. All right, let's do this. I think we're pretty good with the vertical translation. Like, we know that a plus d means up d units. And we know that a minus d means down d units. Okay. Richard, can you clarify what you mean about only for the stretch and not the compression? Oh, okay. So you could say a compression of 1/3, like the reciprocal of 3 is 1/3. So some people say if you're going to use the word compress, then you can say compress by 3. Or you could think about it like a stretch of 1/3, which is really shrinking it by 1/3. So what I'm thinking, because someone had asked like, hey, can we do an example, is let's do this. Let's take example number 8, and we're just gonna go ahead and do number 8 on the graph that we have up here on the grid, so we can practice the graphing and talk about the order, okay? So if I have f of x, and let's actually make this a negative, okay? So the equation I want us to graph is f of x equals negative log of x plus 6 plus 1, okay? And we're gonna graph that on the grid above. So if we think about the graph transformations in order, I know that there are 3 of them happening. What's the first transformation to happen? Yeah, it's going to go to the left 6. So left 6, okay? Now, what happens next? Reflection over, okay, which one, the X or the Y? Yeah, it's a reflection over the X-axis. Okay, so a negative A means a reflection over the X-axis, and then our plus 1 is the last one, which is just up 1 unit, okay? So when I think about sketching a graph, here's sort of how I work it. I don't draw the whole parent function in the beginning, but I draw my center point. So I know that 1, 0 is my center point. And because that's sort of the one nice point on the curve, that's the one that I move left 6, I reflect it over the x-axis, and then I move it up 1, okay? And then I draw my shape around that point. So the first thing I'm gonna do is I'm gonna draw that center point, move it to the left 6 units, so that's gonna get me to here, okay? So this pink dot is the new center point after I move it 6 units to the left. Then, if I reflect it over the x-axis, does that point change or not? Yeah, that point doesn't change in this case. So the green dot is actually going to stay in exactly the same spot. Okay. And then last but not least, we got to move that point up 1. So then the green one stayed. If we move it up 1, now my quote unquote center point is at -5, 1. Okay. The next thing I do is I sort of imagine my asymptote, my vertical asymptote. If I move it to the left 6, it was at 0, so now it's going to be at x equals -6, okay? And then the last thing I do is sketch in the shape. So I know that a regular log function looks like this. But if I reflect it over the x-axis, it actually should start up here and then kind of go like this. Does that make sense? Or is this helpful in sort of determining how to graph the different points? Yeah, for sure. Okay, so the original vertical asymptote was here. Okay, so this is the OG vertical asymptote. We got it at x equals 0. Of all of the transformations that happen, the only thing that changes the vertical asymptote is when we move it side to side. So this +6 changes the vertical asymptote by moving it 6 to the left. So if you were at x equals 0, then it goes to x equals -6. Our center point is at +1 because of the +1 at the end. It moved it up 1. Okay. Let me make sure I got all the questions. Okay, so April, we got the center point. Ethan, okay, that made more sense. Good. If you have already moved the center point, how do you show a reflection on the y-axis? Okay, so let's do one of those also, Eric, to kind of answer your question. Right, okay. So one of the things with the exponential and the log functions is I'm not going to be asking you to graph a horizontal stretch or compression because I think they're not as easy to see. And at some point, it's more about recognizing the bigger features rather than like, oh, let me get this 1 decimal point perfectly right. Now, when we move on after our break to the parent function, some of those it'll be a little easier to see the horizontal stretches and compression. So we'll talk about it when it kind of comes up for graphs where it's easier to see, okay? So Christina, maybe we can kind of hold on to that one for a little bit till we get to some that have nicer numbers, and then we can kind of play with the numbers for that, okay? Okay, cool. All right, so since that was helpful, let's do one more example where we're going to graph one that has the reflection over the y-axis, okay? And then is it going to be too messy if we put it on the same grid, folks, or is it going to be okay? We could put it on the same one. Okay, thank you. All right, so let's create a new problem for number 9, one that might be more helpful. So let's say f of x equals log of 3 minus x, and then minus 2, okay? It's funny because I never used to like make notes in advance for my students because I feel like sometimes you never know what's going to come up in a lesson, and sometimes you just got to scrap what you had and go with the questions that are there. So apologies if this is not super, super neat. But we've got log of 3 minus x equals -2. And again, this is where I'm like, I was so proud of you guys when you were writing this on your quizzes, that a lot of folks were like, oh, this is like -x plus 3 minus 2. But then we have to factor out that negative. So negative parentheses x minus 3 and then minus 2. Okay, so this right here, okay, being able to show me all those steps are super important so that you can then tell me from here what's your C, what's your B, what's your A, what's your D, okay? So from here, I think we can tell we're going to move it to the right 3 units, right? What comes next? What are the next 2 graph transformations? Reflect over the y-axis, perfect. And what about the last transformation? Oh, sorry, Nubia, I didn't see yours there. You're gonna move it down to absolutely. Okay, so right 3, reflect over the y-axis, and down 2, okay? So I'm gonna go back up to my graph, and I'm gonna know that I started at the same center point, okay? Now this center point, I want to move it 3 points to the right. So I'm going to go 1, 2, 3. Here's my new center point. Okay. Now, where is my vertical asymptote after I just move it 3 to the right? X equals 3, beautiful. I'm going to even draw that in for us right here, okay? So this is our x equals 3, okay? So that's the first thing. This is like if I did log of x minus 3. But now, when I have this minus sign here, okay, this reflection over the y-axis, I actually wonder if it would be better to say like this. Reflection over the quote unquote y-axis. what we're doing, and this is only for logs, our y-axis is really our vertical asymptote, okay? This is not going to be true for all functions because some of them don't have vertical asymptote, but we're reflecting it around our vertical asymptote in the log function, okay? So what does that look like? If I go back up to the graph, what that looks like is this pink point now moves to the other side of the vertical asymptote. So it's going to be right there. Okay. So you can almost imagine that instead of having one that looks like this, it actually gets reflected. And now it looks a little something like this. Now our last graph transformation is we're going to move down 2 units. So I'm going to take my green X, I'm going to move it down 2 units. And that's where I'm going to say, okay, here's my shape. And then that is my graph for log of 3 minus X minus 2. All right. So how we doing here, folk? Kind of making sense? A little bit more helpful? Still totally confused? Where are we at? Okay. Processing. Totally fine. Okay. So let's do this. We're actually going to pause here for the, yeah, I'll answer that question in 1 second, April. So we're going to pause here after I answer April's question. We're going to take a break. When we come back, we're going to take a look at the parent functions part. So if you look in Canvas, there's a special tab for parent functions, and there's a whole lot of pages, and we're not going to do them all today, but I do want to sort of highlight a few of the important things there before we move on. And then, so before we do that, let me just answer April's question about where I got the X from. Okay, so April, are you okay with like our starting point moved from the blue point to the pink point? Like this pink point? Yeah, okay. So then the reflection part means really we're reflecting around our vertical asymptote. So where does that pink point reflect to? Well, it reflects to the green X. So this is our reflect over our y-axis. Okay, so I know it's not the actual y-axis, but it's sort of like our new y-axis. Wherever we moved our vertical asymptote, we're gonna reflect it over that point. Yes, that's because our b value is negative, exactly, okay? And then the last thing we did is we moved it down 2 units because of the -2 at the end of our equation. So I'm gonna let folks sort of marinate on that a little bit. I think it's a good time for a break. Let's see, what time is it? All right, so it's 10:50 2 right now. Let's be back at 11 o'clock, and then we'll pick up with the parent functions 1 and talk a little bit more about like maybe how we graph our horizontal stretches and shrinks, okay? So I'll meet you back here at 11 o'clock, and we're gonna be working on the parent functions note.